Hey kids, alright, this video is about inverse functions, and we've already learned about inverse functions earlier in the year, but it's been a while, so we're going to review it, and we're going to apply this to the quadratics and square roots that we've done recently. So as a review, to find the inverse of any relation or function, all you have to do is switch x and y. So let's do an example. Alright, so let's find the inverse of f of x equals 2x plus 1, and you guys know that f of x in this case is the same thing as y. So when we switch x and y, we're going to put an x here and a y here. X equals 2y plus 1. And then all we have to do is solve for y. So we're going to take away the 1 and divide by 2. So we get y equals, and then it's 1/2 x minus 1/2. That's the inverse function of this one. So we would say f to the negative 1 power of x, because that means inverse function, equals 1/2 x minus 1/2. And if we were to graph these on a number line, the original function has a y-intercept of 1 and a slope of 2. And so I'm going to have a hard time drawing a straight line with this stylus, but it's going to look like that. And then the second one has a y-intercept of negative 1/2 and a slope of 1/2. So that one's going to be kind of difficult too, but it's going to look like this. And as we talked about before, you may or may not remember this, but the inverses always reflect over the line y equals x. They are reflections over this line. They will cross right there on that line and be mirrored all the way across. So that's inverse functions. That's this inverse. It's a linear. Let's try one that's quadratic. Easy enough. Let's do f of x equals x squared. So if we switch x and y, we get x equals y squared. And y equals plus or minus, because we're solving the square root of x. And when we graph these guys, it looks like this. Y equals x squared is our parabola, 1, 1, 2 squared is 4, 3 squared is 9. And I think I'm doing alright with the stylus today. That's y equals x squared. And then y equals plus or minus the square root of x. And we talked about this. We have 1, 1, we have 4, 2, we have 9, 3 up here. And then it just mirrors because that's the plus part. And this is the minus part. So it looks like this. And if you were to reflect these over the line y equals x, they would match up. So that's the inverse of the quadratic. However, we talked about this before, that this inverse is not a function, because it does not pass the vertical line test. Or if you had just applied a horizontal line test to the original would have failed a horizontal line test, telling you that when you flipped it, the inverse would not. So the way we can do that, the way we can change this to become a function, is to limit the domain. So if we were to restrict the domain of f of x equals x squared, if we were to restrict that to non-negative real numbers, then our inverse would be a function. And so let's look at what that would look like. So this time we're graphing f of x equals x squared, but only for the x's that are greater than or equal to 0. So we're going to show 0, 0, 1, 1, 2, 4, 3, 9, and so on. But we only show, wow, that's terrible. We only show the right-hand side of the parabola in this case. And when we find the inverse, then we're not going to do plus or minus, because when you find the inverse, the domain of your original then becomes the range of your inverse. And so we already did this. We know that it's y equals the square root of x, but our range, so our y's, have to be greater than or equal to 0. So that means we're not going to do plus or minus, because that would make the negative would make it less than 0. So now we can call it a function. We can say the inverse function of x equals the square root of x. And when you graph that, That's what we've been looking at in this chapter, and that's only the positive part. And so they are still reflections of each other over the line y equals x, and they are both functions now. So in order to keep your inverse a function, you have to restrict your domain. Let's do one more example of that. Okay, so we're going to start with f of x equals the square root of x minus 2. And without even writing a restriction, you guys know that the domain of that is everything from 2 to infinity, because that is the standard square root graph shifted to the right 2 units, and so the end point is at 0, 2. So we know that the domain is restricted here. That means that when we switch x and y, and we say x equals the square root of y minus 2, and we square both sides, x squared equals y minus 2, and add 2, x squared plus 2 equals y, that our inverse, our f to the negative 1 power of x, is going to be x squared plus 2, and our range is going to be restricted from 2 to infinity. Now, the thing about that is, on the original, the range was restricted also. The range was all y's that were going to be greater than or equal to 0. 0 to infinity. So that becomes your domain here. Domain 0 to infinity. We're only going to plug in positive x's now. So let's graph those. The original function is the square root of x minus 2, so it's a square root function shifted to the right 2 units, and then our home base points are all just shifted to the right 2 units as well. So 3 minus 2 is 1, and the square root of that is 1, and then we can go over 4 and up 2, and we can go over 9 and up 3. That's going to be f of x, the square root of x minus 2. And then when we find the inverse of that, and we do x squared plus 2, we're not going to do the entire parabola, we're going to restrict it to only the positives. And so if I plug in a 0 and then do 0 squared plus 2, I get 2. And if I plug in a 1 and do 1 squared plus 2, I get 3. And 2 squared plus 2 is 4 plus 2 is 6. And 3 squared plus 2, 9 plus 2 is 11. So then you have this. And you only have the right-hand side. Because you do need it to be a reflection across the line y equals x. We don't have a bottom here, and we don't have a left side here. And that domain and range, the restrictions are what keep that in place. Alright, and then the last thing I'm going to take you through, we've already done this, but we're going to talk about how to verify inverses again, just in case you happen to see it in the future. Okay, so to verify, and that means like if the instructions in the test or whatever, if it says the word verify, that two functions are inverses of each other, you don't just find the inverse of one and say, look, it's the same as the other. You're going to plug in one into the other, f of g of x, and then plug in g of f of x. You have to do, see that and? You have to do both. And both of those will equal x. And if that's true, then they will be, it's true that they are inverses of each other. So let's verify that f of x equals 1/2 x plus 2 and g of x equals 2x minus 4 are inverses of each other. And just by looking at them, you can't really tell that well if they are, if they're not. But if we just plug the g function into the f function, so 1/2 times 2x minus 4 and then plus 2. So we have half of 2 is 1x, half of negative 4 is minus 2, plus 2. X minus 2 plus 2 equals x. So it works when we do f of g of x. Here, I'll write that, f of g of x. We also need to do g of f of x. And yes, you have to do both. If you do one and it works, that's great, but you need to check the other. So we've got 2 times, and then 1/2 x plus 2 in place of x, and then minus 4. We distribute. 2 times 1/2 is x. 2 times 2 is plus 4. Minus 4, x plus 4 minus 4 is x. So when it says verify, you need to show on the paper that you've plugged in f of g of x and g of f of x. You must show it on the paper. Alright, and that's it for this lesson. Except then, of course, we have this picture. You think this is at Target? You think they did that on purpose? I don't know. All right, good night.